So my name is Clint Nash, and I work at HKS. My colleagues and I are here today to talk a little bit about Toyota Stadium. There's really a ton we could talk about with this stadium, with the design of this stadium, but we're really going to focus on the roof structure and kind of the complexity of the roof and some of the modeling techniques and things we did there to get this thing designed and out the door. And first, I'm going to take a look at the history of the stadium, some of the previous work we had done there. Then I'm going to look at some of the design drivers for the new stadium and the renovation that's currently occurring. Then next, we'll go in some of the computational design, and Sooik will talk about that. And then we'll get into some of the truss details and steel connections that Ryan really worked on. So he'll talk about that last. Okay. As mentioned, my name is Clint Nash, born and raised right here in Dallas, Texas. I have my bachelor's and my master's from A&M, Gig'em. Currently living in Lake Highlands. I have my wife, Marla, and I have a son, 11-year-old son, who just started school today, thank goodness, because it was time. It was time. Started 6th grade, so we're excited about that. And I'll let my colleagues introduce themselves.
Hi, well, my name is Sooik Cho. I'm a former member engineering training too, and I joined at HKS like 2.5 years ago. Before I studied architecture in Han University in South Korea. And I came to the United States like 4 years ago for study the structural engineering to get a master's degrees. Thank you.
Hello, I'm Ryan Ganey. I'm the studio technical leader for the structures group at HKS. Went to University of Washington in Seattle for my undergrad and master's degree. Spent the first half of my career in Seattle. Moved down to Dallas about 5 years ago and have been with HKS ever since.
So a little bit about our structural group. Our structural group at HKS was founded in 1977. Currently, we consist of 49 engineers and drafters. We almost doubled in size over the last 5 years. 3 primary offices, one in Dallas, Houston, and Chicago. And we're currently licensed in 48 states. I think the only states we lack are Rhode Island and Maine. So that's just kind of our state licensing map. Everything you see in blue, along with Texas and Wisconsin, is where I'm currently licensed as a P or SE. So I don't know how many people have been out to the current Toyota Stadium, but the current look of the Toyota Stadium you can see here was built in 2005. We did this also as 2005. In fact, when I was interning at HKS in 2004 and 5, I spent a little bit of time working on this during the construction administration phase. So the stadium was originally built under the vision and leadership of Lamar Hunt, the Hunt Sports Group, in partnership with the city of Frisco. Lamar Hunt was really one of the early founders of the MLS and really one of the key players in helping bring soccer to America. So opened in 2005, as the home of FC Dallas, a Major League Soccer team, the stadium was part of a broader effort to bring professional soccer to the DFW area, and was developed by the city of Frisco in partnership with local investors in the Hunt Sports Group. The stadium original seating capacity was at 20,500 and features a very soccer-specific design around the pitch, really allowing for excellent views and excellent viewing experience wherever you are in the stadium. Over the years, Toyota Stadium has really hosted a number of events. They've hosted concerts. I think Jimmy Buffett used to have an annual concert out at the site. The Division 1 AA, formerly FCS, college football championship happens here. I think it's happened here for the last 15 years. High school football games, I think a rodeo event, a number of things besides MLS soccer games. On the south side of the stadium, HKS designed the National Soccer Hall of Fame, which opened in 2019. This is really the only side of the stadium, which you can see on the south side at the upper right, and down in the right-hand corner. This is the only structure out there that's going to more or less remain untouched. Everything else is either being renovated, demoed, and completely rebuilt. So the driver behind this was really since 2005 when this opened, a lot's changed with the MLS. One, the MLS has just grown significantly in popularity in the United States. And then really every MLS team now has a very dedicated stadium to that team. That was really in 2005 when our stadium, or when the original Toyota Stadium opened. It was known as branded as Pizza Hut Park. It was really at the forefront of the MLS. It was one of the first dedicated only venues for an MLS team. But since then, the popularity has grown. And as you can see, just in the last 6 years, I think they've added 6 new stadiums. And one of the requirements since 2021 is that every seat, or actually not every, 90% of the seats at the stadium have to be covered, have a drip line and coverage. So you can kind of see that there with all those different stadiums. I think Columbus, Austin FC, FC Cincinnati, I believe that's St. Louis, Nashville, and New York. All of those stadiums feature a roof that completely covers 100% of the seating. So this was really the big design driver to alter the stadium, which had no original roof in 2005. You can kind of see that there in the top left. That's the current stadium. So on the east side of the stadium during the game, you had absolute 100% exposure to the sun. So you got baked, especially in these Texas summers. The west side had coverage from the press box, but primarily the biggest driver was trying to shade the east side and try to provide coverage and a drip line over all the seating. Patron comfort, patron amenities, broadcast and technology upgrades, along with this general venue logistics were all drivers behind what we were doing here. And so a lot of the early time, which we'll get into a little bit, was just talking about how can we actually add a cantilever to the existing structure, or a roof to the existing structure, what pitch does it have to be at, what length do we need to make the cantilever to actually shade the east side. So we did a lot of early studies with Manhattan as a pre-construction contractor to actually try to put this roof structure on the existing stadium. But when we got down to it, it was just too cost prohibitive. There was significant upgrade that were going to be required to the columns, and a significant amount of work that's required for the foundations to upgrade. So based off that analysis and that early pre-construction work we did with Manhattan, we determined really we just need to take out a lot of the existing buildings and rebuild with a brand new roof structure. Wait, what? No, in 2005, there was no allowance made for a future roof. So early on, we really looked at a lot of different options. These are kind of the 3 main options that we looked at, but it's not by any means limited. These were just the 3 primary that we kind of looked at. One was a primary 3 large roof trusses that span between 4 corner columns that you see at the top left. We then looked at a ribbon structure that, as you can see at the bottom left-hand corner, a little bit more organic form. And then we also looked at this swoosh structure, which is ultimately where we ended up, and which really is the Hunt ownership group in the city of Frisco really wanted the swoosh look, something a little bit different than what some of the other stadiums had. So once we got to that point, they decided which direction we were going to go. Our architecture team, along with our structural group, spent a significant amount of time just analyzing the truss conditions, roof heights, cantilever lengths, really trying to maximize the amount of shade we could add to the existing bowl structure. And I should say, all that existing bowl, everything that's kind of down on grade, the seating on grade, the pitch, that's remaining as is. We're not doing a ton of that. There is some renovation we're doing in there, but most of that's remaining as is. Everything we're doing is really demoing out a lot of the existing 2-story structure around the stadium and building back a new press box, 3-story structure, so it's an additional story, and this entire new roof structure. So we also looked at various iterations of the swoosh option in and of itself. As you can see at the top left, which is kind of a more organic and rounded form, that was one of the early phases we went to. The bottom left-hand screen, we actually at one point talked about putting the fabric awning that you'll see in these further renderings on the underside of the truss and really hiding all this truss and the steelwork. We actually went away from that because Clark and Dan Hunt from the Hunt Sports Group, they really wanted to expose the structural steel. You'll see it in a little bit. They want to paint everything red and really showcase what we're doing out there, which is unique for us. And it's really a unique part of venues in general, is you get to showcase a lot of the steel framing that oftentimes gets hidden. So the top right is kind of where we landed in concepts and SDs, but with very segmented roof structure, the swoosh form, less organic, more flat roof surfaces. And then we pitched it all and put an elevation on the ends of these cantilevers to allow for maximum shading of the entire structure. It wasn't related to Nike or any. We just called it swoosh because there is some resemblance to that. There's no relation at all to that. There was no design relation, and really it was an architectural feature that the Hunt Sports Group really bought into. So early on, really where I kind of leave off to guys who are much smarter than me and who can talk much more intelligently about the final design of this, which is those two. I was doing very early conceptual SD and DD studies with just a 2D frame analysis, trying to get myself 80% of the way there, trying to understand what options we have to actually make these 100-foot cantilevers work, 100-foot plus really cantilevers work. So you can see those at the bottom are really early. I think those are early Revit models where I was working with our BIM team. I was doing a frame analysis, 2D frame analysis, getting myself 80% of the way there, feeling comfortable about sizing, and then I'd export that into Revit. And then our BIM manager, who's Greg Vasquez, who's not here today, he actually took that and then he was able to import it into Revit, put it in the Revit model, the BIM model, let our architects know, hey, go take a look. And they were able to visualize it and see it conceptually and then make a determination on which one of these features or which one of the trusses they really liked aesthetically. Those are just 4 options of ones we discussed, but by no means are those all. We did a ton of renderings. We also looked at a 3D truss versus a 2D truss. Another item that we determined very early on with Manhattan as a pre-construction contractor is the 2D truss was, even though it was heavier, was significantly more cost effective than the 3D truss in terms of shipping, fabricating, painting, and erection. So we ended up going with these planar trusses, which we'll see in a little bit, and Sooik will talk about a little bit more. So on the left-hand side, you see that's what the current stadium looks like. You see the full kind of sun exposure on that east side. This is from the north looking south. And then a similar view, the final condition on the right, that's just a rendering. But you see all the red steel, all the painted red steel, fabric awnings, and the louvered steel work at the backside here. And a similar view. So one of the really unique things we're not going to talk a lot about today, but on this north-hand side, all of that structure is built over existing three-tier retaining wall, retaining approximately 28 feet of soil. So there's a ton of work that went into just the below-grade portion of this and building these structures and this new roof structure over existing buildings, which again it's a whole other presentation, but there's a lot of work that went into just this whole site. Pretty much everything you see in this image is new, minus some of the outside buildings which are being renovated at the corners, but everything else is more or less brand new. And then you see the Hall of Fame at the south end of the top of the screen, but the south end of the stadium. Ton. We more or less all the existing foundations were abandoned. In fact, the column grids were set based off some of the existing foundation locations to avoid them. The new column grids, I should say. And that's just an overhead view of the stadium. You see kind of the swoosh, the new roof structure, the drip line really covering all of the east and west and almost all of the new north seating. And then north of this, there's tons of new soccer fields that are out there existing for youth sports, all sorts of things. This is really an epicenter for DFW for youth soccer. And that's kind of a view coming in from the north entry. You see all the exposed steel, the red structure. So obviously highly aesthetic structure and highly visible.
So that's
Yes. Yep. It's just a completely fabric supported on steel structure. And Sooik will talk a little bit about that here in a minute. Okay, go ahead and get it.
Okay, I'll a little bit more talk about the parametric design part. So one of the big challenges of this project is even in the concept phase and the schematic, and also in the design development and the construction phase. For example, in the earlier phase of the concept design and schematic design phase, we want to give a relatively quick response what the structures will look like, what is the tonnage will have, and running different calculations in a really quick phases. And also there's a lot of challenges. There's existing conditions, so we don't have a full freedom where to put the columns, all those kind of items we have to consider. That's why we were expecting to have a lot of changes in terms of geometry and design. That's why we decided to go with the parametric approach. So for example, the screen, what we're seeing is the direct export from the Revit model. So for example, we grab all the drawings from the Revit and also like the frameworks and bring into Rhino. And then we start to use this as like an input. So later on, once we change the Revit model or architecture model, we can quickly change our roof structure as well. One of the item was like one of the group of architects were only working on the building. So there's like a continuous changes. For example, where the column comes down, where does the lateral system is located, where does the expansion joint is located. There's like a different changes. When we go to the next slide, there's a different group of architects also only working on the surface itself. So they typically go work in the Rhino to accommodate all the shading for the stadium. For example, the tip of the elevation of the roof is like not really constant because of the we need to get the shading to the other side of the stadium. So throughout the design phase, even like in the CD phase, the elevation has to keep change, and we want to accommodate those. Like small change might not be like a big impact on the structural, but the small change start to accumulate, we start to get lost. What's the behavior of the structure itself? And also sometimes small change has a big impact on the structural response as well. So we want to kind of accommodate the design changes on the structural analysis as well.
I think one of the key things about this too is they would give us kind of model, no weather model. We really created roof surface based off of the Rhino model. Very limited input production.
Yeah, and for those of you not familiar, Rhino is a 3D modeling software. It's a geometric modeling software that you can create inputs and equations to create these curved surfaces.
Mm-hmm. So what we did is grab all the existing Revit drawings and the framework, use as an input, and also the surface we got from the architects. So for example, we start to use this as like a where's the column is located, where's the tip of the roof is located. So we generate like a grasshopper script. So what happens is later on, like after a week or two, if there's a change on the building side, we just need to re-import, and then the script will automatically generate all the geometry in a second. Another thing is, once we bring all the Revit model, which will define the support of the roof, which you can see in the point that is supported on the column, and also the tip of the roof, we just have to fill with the truss system, and then we assign as a different variable. So later on, we can change like from 2D truss to 3D truss, all different kinds of design variables we want to control. And then another thing is, another challenge was like, as you can see here, the grid line from the building starts to turn, and then the northwest corner. Where the grid line, building grid line turns is different from where the roof grid line turns is different. I mean, the turn location was different, so we have to accommodate within this area of the northwest roof. And that's why we had to use like a transfer system to accommodate the building difference between the building grid line and then the roof grid line. And then we had like an input parameter to like adjust a little bit, like left and right, to accommodate the transfer location of the trusses. And one of the benefits of using the parametric design is you fully are dealing with like a data itself. So what you need to do is define all the nodes you need in terms of structure. And after that, you just have a connectivity. Well, in each member, which member is connected to which node to which node. So one of the problems always like moving from the Revit model to the analytic model is like dealing with the tolerance of a different software. Once you bring it in, sometimes just like everything, like members are gone, or parts of the members are gone. Using the parametric design, we're only using the data itself. We have like a clean, smooth transition from the Rhino Grasshopper data into the analytic model. Right now, we use the Restock 3D because Restock 3D has the capability of like a copy and paste of data directly into it. So once we have updated geometry in the Rhino Grasshopper, we can build the whole geometry in a second in the Restock model. Obviously, we do have to go through like a different boundary conditions and the umbrage line. We have to assign those. There are definitely input required from the engineers, but over the complexity of the geometry, we can just directly use the data and directly bring into the Restock model. And this shows like a very concept level and the schematic design level of like different design schemes. For example, we start with like a studying of like, let's say, a 3D roof truss with the curving roof structure system itself. So we first build the script to generate the roof and the structure itself. And then later on, we can study a different type of a 3D geometry, like whether the surface might be attached to the below. And then going on, there's like now we are building the full 3D model, like a switch type, as you can see in the ribbon type and the different types of it. And one of the benefits of like computational design and parametric design is once you build one working script, you can just copy and paste and adjust a little bit. And you can provide like a quick response on the architecture. So architects can use this for the rendering, and also we can calculate the tonnage at the same time. Using the Grasshopper script and this parametric design approach, we were able to like study 2 schemes per week, and like on average in a very speedy way. I'm going to go a little bit detail on how we set up the overall parametric. For example, as I mentioned, where does the column location, which is the building column location, was one of the inputs. So I bring that up. And also one of the input was the roof tip point, where does the elevation wants to sit. Between that, we have a lot of different parameters we want to control. For example, like a slope of the trusses or depth of the trusses. Sometimes it's like limited by the transportation of the overall truck itself. And also how many bays or how do you want to have a 2D or 3D trusses. So between the column points and the roof tip points, we have full freedom of design. And then here comes a little bit more important of like what design parameter do we want to control? Because theoretically, we can have like hundreds of different parameters and becomes extremely complicated, and it's like become not practical and not intuitive. So there here comes like a important of like a senior engineer's insight, what kind of parameter we want to control, what kind of parameter we're just hard coded and use it as it is. Another benefit of using the computational parametric approach is this is like we have to add a catwalk in the construction design document phase. We already have all the full running model and already designed, but we want to attach this full catwalk, and then you will get more wind load on it. So what we did is architects lay out all the catwalk they want to have. We model in the Revit model, and then bring it into Rhino, and then using the script, we generate the analytic model and just attach it. And it has like a very smooth transition. We don't have to manually adjust the existing analytic model. That will take really a lot of time to adjust those. After like building the whole analytic model, we ran the eigenvalue analysis to prepare for the wind tunnel analysis, wind tunnel testing. So for example, let's see in the first mode, you can see that there's like a longitudinal movement that's the dominant. That's because we have a moment frame in this direction. In the other direction, we have the brace frame. So that it's reflecting on the eigenvalue analysis. That moment frame gives like more softer value. And once you go to the second mode, you can see start to see the vertical movement of the north and northwest roof structure itself. That's because we have like a transfer system. That's why we start to have like a vertical move, not only the translations. And then if you go to the third mode, in the fourth mode, you start to see longitudinal translation and actions, and also the vertical movement as well. So we send out all the eigenvalue analysis data to RWDI for the wind tunnel testing. RWDI built the stadium model and the surrounding. I believe this overall diameter is like almost like a 15 feet wind tunnel model. And then they 3D printed the whole roof structure itself, and then attach the pressure tap to get the wind loading.
Yeah, I think don't get the scale of how big that tunnel is. That red model, the little red dot you see on the sides, probably 3 feet wide. I mean, literally that table's 15 feet, and then they have all the other structures around the side in those little white boxes represented there, and then they can rotate that table 360 degrees and see wind flowing all over it and gives wind pressure to the stadium itself. That model is actually at HKS, so you get HKS. See us on the 6th floor and take them to the model. So really good.
So as a result of the wind tunnel testing, RWI gave a different wind pressure, and you can see it's a different region of the wind pressure we got. So we were able to see it in some. Yes.
Clouding and also picturing
Pedestrian like a comfort.
and emergencies proceeding was something that would make someone uncomfortable cities.
So the model was built up plastics.
Yes.
And so you just have little sensors on the spots will make the pressure.
Yes.
And then I think RWDI gave us an opinion after that we were sending all the period and the frequency of the building. We did not have like much of a dynamic amplification, so that's why we just used the static pressure approach. So after getting this, we were able to see like some high pressure region. We were able to see like 30% reduction in the wind load compared to the cold wind. But for ASC wind tunnel chapter, we were not able to reduce further than 80% of the code base. So some area eventually we had to bring that up the pressure, but yeah, this is what we get. Also, one of the benefit of the parametry was all the loading was also assigned as a parametric. Once you get the data, RWDI gave like 4 different road cases based on the directionality of the wind. We were able to easily just copy paste all the data and bring into the analytic model.
They should feel better about the ACE. All the winds are generally much smaller. Makes it really good our size. Easy code.
Another part is overall surface is covered by the fabric structure. We closely work with the ETS, the fabric engineers. All the fabric or pre-stress, so it can be a little bit more stiff. But the pre-stress meaning all the reaction has to go in the roof. So we have to assign the loading, the pre-stress loading into the structure itself as well. So what we got is like a result of the final element. They have a discretized point and the point reactions. I mean, we can definitely directly use this and then manually calculate the equivalent loading. But instead of doing that, we just bring all the data into the grasshopper, and then we want to visualize what is the different case of the loading we have. So you can more intuitively understand what kind of loading we're seeing, and then we can just directly use like a result force into the analytical model. From now on, here Ryan will talk a little bit more on the truss design and detailing itself.
So Sooik talked a lot about the analytical model. So he built this analytical model to determine the loads on the structure. So the next phase in the design is we have to size the members and design the connections. Here's an overall plan view, and we've kind of heard north, west, east. This kind of gives you an overall idea of the structure. The roof was split into 3 different structures. You have the west and the east, which are mirrored over the pitch and are actually very similar to one another. And then as you turn the corner, the north side, that's where the scoreboard is, and it kind of, that swoosh area, and it comes to a point. A couple items I want to highlight. The dashed lines are the truss bracing. So we had to connect all the trusses to prevent racking and to resist those fabric loads Sooik talked about, wind loads, and thermal loads. And then also an expansion joint. We actually split the west and north separate from one another because it was too large as one structure and the thermal loads were getting too much. So we put an expansion joint to kind of allow the 2 structures to breathe, and especially because this is an exposed structure in North Texas, we have very large temperature swings, as you all know. Going back to the computational design, we're able to use this to figure out forces. What we're able to do is using this Grasshopper script and Rhino, we're able to visually look at the forces. For instance, we could type in, I want to know what the maximum force of an HSS 8x8 is. And it would highlight all the members and give us the maximum force. And we could easily find which member had the maximum force. Or we could say, give me highlight all members with a force over 100 kips. This allowed us to efficiently group members and efficiently pull loads to size connections. Now I'm talking about connections. For those of you who are structural engineers in Texas, know that the standard practice in Texas generally as a structural engineer of record is to delegate the connection design to the steel fabricator. However, on this project, the connections were extremely important. As Clint and Sooik both talked about, the connections are exposed. So there's an architectural aesthetic component. And they're very unique. You can't just pull these connections out of the ASC manual. They're not a simple shear tab, not a double angle connection. So as the engineer of record, we decided to take on that responsibility and design the connections ourselves. Here's a typical truss elevation. This is the east and west truss. Most of the trusses look like this. We used a W18 top chord and a W14 bottom chord. with an HSS vertical and diagonal web members. You'll notice the gusset plate connections for the web members in the lower left here. Again, we sized those gusset plates because we were concerned with how they would look. We didn't want to delegate that to a fabricator and then have something that the architects weren't happy with, was what we weren't happy with. And so we wanted to express those connections. So we designed those. And the gusset plate connections were very angular to kind of go along with the angular form of the roof truss. In terms of, and then at the tip of the truss, we have a gusset plate as the truss comes to a point, a nice gusset plate to kind of end it. And then the top cord shoots over from the edge and cantilevers over a bit. The splice locations, you can see this on the elevation, the highlighted circles, those are all the web splices. So the truss, working with Manhattan early on in design, we figured out from a constructability standpoint, how many pieces of the truss needed to go in place. It was split up into 4 different pieces, as you can see, 2 in the back and 2 in the front. The cord splice was a typical a bolted splice plate, top and bottom on the flanges, and a web splice plate on the web.
I think when we worked on this to make sure that one, ISIS were they the tonnage was enough for the crane, because they're also lifting over. You can't get on the pitch over some existing buildings. Actually, correctly. So the tonnage of the truss and the weight of it's critical for the actual erection process. And then also the use of wide frame. And that was a heavier member. We actually used heavier members, but reduced the cost of the project just because we use wide flange members for spools, and it's a little bit harder to cut.
What is the thing that
Why do we choose those? Oh, I think they're around, the 14 was, it varied depending on the truss, but it was around 200 pounds per linear foot for the 14 and like 170, 150 for the 18. So, and then talking about the erectability and the constructability, one of the items that we worked on with Manhattan was how the truss interacts with the building. And it was really important to create a splice location above the roof. So what the contractor can do is build these buildings, finish out the buildings, put the roofing on, and then put the trusses on top. So as you can see in the details, there's a splice plate that's about 2.5 feet above the roof. So the roofing can come in, flash up against the column element. We actually added side plates for easier flashing. And then the truss is almost decoupled from a constructability standpoint and then can sit on top of those columns that are above the roof. And then, as Sooik mentioned, there was, as you turn the corner from the west end towards the north end, there's a transfer condition. And that was due to some column locations not stacking with the trusses due to visibility from the seating and the suites below. The way we accomplished the transfers, we had a really heavy I think it was a W36 member. It was probably the heaviest beam we had on the job, heaviest member on the job at the front. So the truss sat on that member. And then on the back, we were actually able to add some bracing, you can see in the 3D view. So the back connection, actually the load went right through that bracing and we didn't have to do it through a transfer beam situation there. Right. Yeah. Yeah, that's the locker room tunnels, right? Right. So locker room tunnels, we were limited by where we could put the columns. And then as you turn around the north end, this is the scoreboard area. Sooik kind of talked about the modeling of that scoreboard area from an analytical perspective. So these trusses were a bit different from the other trusses, that they actually sat on a single column. That's a 36-inch diameter by 1-inch thick steel pipe that comes up. It's got a bolted connection up at the top, bolted flat plate connection similar to the connections at the building. And then that pipe was sized for the bending moment because the top cord comes around the back end of the truss and is imposing a lateral load on that column. So there's careful selection of that material to make sure it would work. And it's all exposed. So the architects wanted a big, nice round column for that exposure. Next section here, I want to talk a little bit about the truss bracing. Now, I mentioned before, we had to connect all the trusses together to prevent them from racking, to resist that racking load. That racking load came from the fabric support itself thermal movement, and of course, wind loads. Now, one of the things we thought about is when you're connecting these trusses, we want to allow them to move up and down independently of one another. If there's a wind event, we don't want these horizontal members restraining the trusses. So we really want a pin connection for that horizontal HSS tube into the truss top and bottom cords. So as some of you know, a pin does not have a lot of erection tolerance. I believe AISC, the maximum hole diameter of a pin is 1/32 inch larger than the pin itself. So that's no erection tolerance at all. So the way we're able to get around that and solve that issue is we used a bolted end plate, as you can see in the upper right detail. So that pin would be shop attached to the rectangular HSS member that spans horizontally, and then that connection or that member can come in and get bolted in the field. And that end plate allows tolerance for shims and slightly oversized holes in the bolts so they could erect these trusses and erect the bracing in between them. Then, as you move along the truss, there are areas that I mentioned in the overall view of diagonal bracing. And these diagonal bracings, we did have full bolted connections because we designed those trusses to kind of move together. And that's what's going to drag the load, that horizontal lateral load, back into the building and into the foundation system. We used the diagonal bracing, our pipe, HSS rounds, so circular members, with a bolted connection to gusset plates. At the cord connection, the gusset plate is shop attached to the cord element, and then the diagonal braces come in and are bolted with that knife plate connection, and then the horizontal comes in with an end plate connection. So those are all independent pieces that they come together. All these connections are bolted and for ease of constructability. We did not want it was not feasible for the contractor to get up there and weld all these connections together. And then at the horizontal connection areas, we needed vertical bracing to make sure those trusses moved as a unit and could resist those lateral loads. The vertical bracing is very similar to the horizontal bracing, but we used a square HSS tube instead of a round. And you can see it's a similar bolted connection. And again, the connection coming into the truss, the gusset plate, the vertical gusset plate for the vertical bracing and the horizontal gusset plate for the horizontal bracing, all fabricated in the shop, all welded in the shop, and then so they can come in and bolt the horizontal with an end plate connection and bolt the diagonals and the diagonal bracing and the vertical bracing with that shear plate connection. Now we mentioned the expansion joint, and so there was some critical detailing that we needed to do at the expansion joint, right? We needed to allow the north section and the west section to move independently. And I believe that movement, so correct me if I'm wrong, was about 1 3/8 inches, 1.5 inches, just to thermal loads. And going back to Sooik's model, he actually imported and put in thermal loading in the model. We had to, normally when we're designing steel, we don't really account for thermal effects. They're very, very small. This structure was so large and an exterior exposure that we really need to account for those thermal loads. The connection we came up with on your left there, we have the typical pin connection to the truss, and then we did a custom seat connection or a oversized tube that the horizontal tube slots into. That whole surface is greased to allow for movement, and there's long slotted holes and some through bolts just for stability. So that was a custom connection, and those, as you can see highlighted in yellow, occur along that joint. And last, I want to just talk quick about the fabric support and how that all works with the truss system. So the fabric panels, they come in, they're going to span from truss top cord to truss top cord. That's where they're going to stress them. And then there's an HSS at the top, at the tip of the truss, and an HSS back at the building line. So they're about, the trusses are 30 feet on center, and they're about 100 feet long. So that fabric panel will be 100 by 30. And so in the upper right, you can kind of see there'll be some anchors that are stressed, and then they're stressed at each top cord. Now there's one other member highlighted, right? So that member in between the truss top cords is more of a hold down member because the fabric can only drape about 15 feet. And when we're talking about stressing it, it's stressing it to avoid the dead load. to counteract the dead load. Because if we just drape that fabric, it would drape too much. So we kind of had to we have to pretension it. And then those pretensioning loads go into the truss system and are resisted by that bracing. And the lower left is a current photo of the Hall of Fame at the south end of the stadium. So you can kind of see what that fabric will look like on 4 sides of the stadium when it's all completed. And with that, we want to thank you all for having us, and we'll open it up for any questions y'all have. Oh, before that.
15 years ago, going through that analysis and getting that many iterations of these trusses, that many options would have been possible. It's really the last 15, 20 years that that's really become forefront of engineering. We can put a bunch of nodes, a bunch of different constraints in that binary grasshopper script to its development to allow us to analyze so many options, give us that kind of real-time just analysis. What it takes me 50 years ago.
Right. Yeah, that quick response.
Weeks, months. Sooik and Ryan really work together. Really good. Cool project. A really great project. So. We worked with the fabric supplier early on, and I don't think they were necessary. We worked with the fabric supplier early on to talk a little bit about that. As far as I know, so the fabric on the north side at the Hall of Fame has been there for now 6 years. As far as I know, there haven't been any repairs there. There was discussion about that if they have to go and repair, and I think there's the ability to do that if something were to break. But I think the intent is that for the last 15 to 20 years, pretty, if not more. So, yes.
Is there a maintenance schedule for this preseason?
No, I think you just do it once and
Yeah.
But they can. I mean, some of them are accessible from the roof, but they would, if they had to recrease it, they'd have to get up.
Yeah, they're not only that, the paint on this, we went through, I think, so let's say $3 million budget is associated with painting these trusses to make it like a high-end, high-exposure paint that's not going to fade, and with a clear coat. So there's a lot of thought that's been put into the maintenance of this because it's not very, it's really not accessible the way a lot of NFL stadiums are with catwalks. You don't have the same thing here. Yeah. It was, and I think that's part of the reason the code doesn't allow you to reduce all the way up to the full RWDI. You know, even on top of the wind exposures, the values we got from RWDI, we still factor those, and there's still some allowance in there for material defects and things like that. I think that's a big part of the reason the ASC code limits how much you can drop down per the wind tunnel study, because of that very issue where you have buildings that are surrounding that could change, will change. We know they'll change, right? Especially in this area of the world. There's just something new up there all the time. So. Yes.
So in parametric design, instead of the entire U-shaped design, why was the current design chosen? I think this was a few slides back.
Yeah, that was really, we studied the U-shaped, we studied multiple iterations. At one time, we even talked about putting a roof over the entire thing. Where we ended up with this design was really chosen by the Hunt Sports Group in the city of Frisco. This is what they liked when they saw it. They didn't really like the ribbon. They didn't like the U as much as this. This felt like two discrete elements coming together. So that was really this architectural and an owner-driven design process. Yes. So they are started demoing all of the east side currently, and they're installing the piers currently as we speak. It's going to be a stage construction. So the east side's going in first, then followed by the west side, and then following with the north side. It's going to be a 4-year process. Yeah, we didn't talk about that, but the intent is to let them play soccer and remain operational during that time. So that's why it's going to be a longer process than normal. Ooh. No, the truss, so the vertical column load I think was on the order of 1,000 kips.
Yeah, it was over 1,000.
Yeah, maybe.
So the was over 1,000. Truss, you know, the front column is going to be compression generally, and the back's going to uplift. I remember the back was around 600 or 700 kips of uplift on the back, but we didn't design that. I would say like 1,300 in the front, maybe 1,200 for the compression there. This also has those. I will sell so then I will create back of the balance and good compression stuff. Yeah.
And the trusses themselves, I think the tip of the cantilever will move under a wind event 5-6 inches.
Yeah.
So it's not, I mean, they're moving. They're not just. Yes. Yes. And we had to reinforce the piers accordingly for some of that uplift. There's actually not as much on the west side. There's not as much uplift as you would think because we do have a 3-story structure that have a lot of dead load that counteracts that, which is the good part of that.
Yeah, that 700 is just at the truss. It gets reduced because there's 3 floors of structure.
Yeah. Any other questions? Well, thank you. Thank you guys for having us. Appreciate it.